Howdy students, this is going to be Unit 9, Bonding in Chemical Compounds. We're going to cover 4 things in this lesson. We're going to cover valence electrons first, then we're going to cover Lewis dot structures, and then we're going to cover Octet rule, and then we're going to look at what happens when elements lose or gain electrons, which we call ions. So the first thing we're going to look at is the electron configuration in an ionic bond, because that's going to help us describe how electrons are transferred. So we need to understand what valence electrons are first, and they are the electrons in the highest occupied energy level of an element's atoms. To find the number of valence electrons, we're going to look at the element's group number. So before I go on, just want to remind you that we have the nucleus in the center of the atom, and around the nucleus we have electron shells. And so what a valence electron, where those are located, those are going to be located on the farthest, or what we call the highest occupied energy level. So whatever the farthest energy level out is, that's where we're going to find valence electrons. And those are going to be responsible for bonding to different elements. So to figure out the actual number of valence electrons, we could go in and look at all the different shells for the atom, or what we can do is go at the periodic table and look for a shortcut, which would be the element's group number. So here on the periodic table, the alkali metals, some tables have it listed as 1A. This column is going to have 1 valence electron. 2A, or group 2, the alkaline earth metals, will have 2 valence electrons. Now what we see here is we go down to 3B in the transition block, but we're not going to go here. What we're going to do is go over to the representative elements, and we're going to go to group 3A, which would have 3 valence electrons, 4A, 4 valence electrons, 5A, 6A, 7A, and 8A, which would have a total of 8 valence electrons, which we call the noble gases. So what we're going to learn how to do is take the number of valence electrons and draw something called Lewis dot structures. We can also call them electron dot structures. This is a system of arranging dots represented by valence electrons. A man named G.N. Lewis developed this system, and so that's why I called them Lewis dot structures earlier. So to help us understand where these dot structures are coming from, we're going to do a little bit of background information. And the background is going to come from Unit 3, which we learned way back in September when we were first starting school. So we're going to look at the electron configuration for phosphorus. We learned things like 1s2, 2s2, 2p6, 3s2, and 3p3. This should sound familiar because it helps us describe where the electrons are located within an atom. So just a refresher, the first number, that is going to be our energy level. And that was denoted by the quantum number N. And N can have values of 1 all the way up to 7. And then we had a letter. The letter represents the shape, which was the azimuthal, fancy word, quantum number L. And that could be values from 0, 1, 2, or 3. S, P, D, or F. And then the last thing we had up top was the actual number of electrons occupying that specific subshell. Okay, and so that's when we saw things like anything with an S can have 2 electrons, anything with a P can have up to 6, D can have up to 10, and F can have up to 14. So that was a snapshot of Unit 3. And then we learned about orbital diagrams. And so this particular electron configuration is for phosphorus. And so if I were to draw it out using arrows in an orbital diagram, these two things right here are equal. They're the same depiction. But what I'm going to do is go ahead and fill in the arrows. So 1s, s's can have 1 line. P-shaped orbitals can have 3 lines. And each line represents a subshell. And each subshell can have 2 electrons in it. So we go 1s2, 2s2, 2p6, 3s2, which is matching above. And then last, remember Hund's rule, you have to put 1 electron in each line before you can go back and fill up the remaining subshells. So this is the orbital diagram for phosphorus. You don't actually have to write these red numbers in here, so I'm going to leave those off. That is just the orbital diagram. So now what we're going to do is write the Lewis dot structure. And how do we get that? We're going to look at the highest occupied energy level. So the highest occupied energy level that I have is 3. That is the highest energy level. So what I'm looking at are these two. And if I look at how many electrons there are, there's 1, 2, 3, 4, and 5. So I'm going to draw the Lewis dot structure for phosphorus. And here it is right here. If we look, we have the element symbol, phosphorus. And then we have 1, 2, 3, 4, and 5 dots. And I'm going to show you how to draw the dots in just a moment. But this is how we represent phosphorus. It has 5 valence electrons. So let's practice. Let's go ahead and draw some dot structures here. For magnesium, the first thing I need to do is figure out where it is, and it's in group 2A on the periodic table. So it's going to have 2 valence electrons. So I'm going to start by writing the dot structure, the atomic symbol. And what I'm going to do, this is what I teach my students in class, is that I'm going to imagine that there's a cube around the atomic symbol. I have 4 sides to the cube, and I'm going to be able to put just 4 I have 4 positions where I can put the valence electrons. So I only have 2. I always start at the top. So I'm going to put my first valence electron there. And the second one, I'm going to go clockwise. So the second one is going to be placed right there on the side. And that's it. So the final dot structure would look like this for magnesium. And then I would be done. Now another depiction that sometimes we'll see is when we have one of the sides is the S block, and sometimes what we see is that the other sides represent the P block. So for magnesium, and I know I'm drawing a lot here, but you might see 2 dots on top and no dots on the side because those first 2 come from the S block, the first 2 columns of the periodic table. Okay, let's go ahead and draw sulfur. So here's sulfur. Sulfur is in group 6A, and so it's going to have 6 valence electrons. So I'm going to start at the top, 1, and go clockwise. 1, 2, 3, 4, and then 5 and 6. Or, like I said, sometimes you'll see the first 2 are in the S block, and then you'll have to use Hund's rule to fill 1, 2, 3, and then come back. So these are actually the same, but sometimes it doesn't look the same. Chlorine is in group 7A, so chlorine would be 1, 2, 3, 4, 5, 6, 7. And it's going to look the same with using Hund's rule on the other. Rubidium is in group 1A. It has 1 valence electron, and these are my favorite because we only have 1 dot on top. Silicon is 4A. So we're going to have 1, 2, 3, 4. Now, silicon, some depictions would have the first 2 for the S block, and then 3 and 4 like that. So sometimes the depictions are not the same. Argon is a noble gas. It has 8 valence electrons. It satisfies what we call the octet rule. I'll talk about that in a moment. It has a filled valence Lewis dot structure. So let's talk about the octet rule. Elements want to be stable. They don't want to be unstable. In forming compounds, elements try to achieve the same electron configuration as a noble gas. Metals will typically lose electrons and become positive. Metals lose and become positive. So if I'm looking at the electron configuration for sodium, here are the arrows, 1s2. And if I was writing it out, it'd be 1s2, 2s2, 2p6, 3s1. And if I was looking at the highest occupied energy level, it would have one valence electron. And it makes sense because it's in group 1a. Neon, which would be the same row as sodium, would have a filled outer valence shell. The 2s and the 2p are completely full. And you'll notice that we've missed an arrow there from sodium. So what happened? Well, let's go back up here. It said metals typically lose electrons and become positive. For sodium to become satisfied and to be like a noble gas like neon, it is just going to lose one electron. Let me go back there for a second. You might have missed that. But when we had lost that electron, sodium becomes positively charged because we lost a negative electron. Nonmetals will typically gain electrons, and they become negative. So nonmetals gain and become negative. We call these anions in an ionic compound. So if we look at oxygen, 1s2, 2s2, and then we have 2p, 1, 2, 3, 4 on the outside there, 2p4. So to become like a noble gas, which is neon, the closest one, it can either gain electrons or lose electrons. Well, we already said that nonmetals gain electrons, so it would have to gain a couple in order to get to a filled outer shell. So if we added 2, what we'll see, we added 1, 2, we'll see that oxygen becomes 2 minus, becomes negatively charged. That is how it becomes like neon. So electron dot symbols that we just drew can be used to represent these ions. So let's go through a few examples. Remember, you can have cation ions, which become positively charged, and anions, which become negatively charged. So if I'm looking at sodium, sodium usually has 1 dot, and to become like a noble gas, it's going to lose an electron to become positively charged. Chlorine, 1, 2, 3, 4, 5, 6, 7, it's going to pick up an electron to become Cl minus. Fluorine will do the same. It will pick up 1 electron to become F minus. Magnesium has 2 electrons. It is going to lose those 2 to become Mg2+. Oxygen has 1, 2, 3, 4, 5, 6 to begin with. And instead of losing 6, it's just going to pick up 2 more. So O would be 2 minus. And then the last one, aluminum, starts out with 1, 2, 3 dots. And instead of picking up 5 electrons, it's just going to get rid of 3 to become Al3+. Now, to draw the final ions correctly, because the metals lost electrons, we don't show the dots. But because the anions picked up electrons, we're going to show them having a filled outer electron shell. Some pictures show just the symbols without dots. But this is how we're going to draw it here. So the cations don't have dots, and the anions will have dots.